is self-attention, theory behind the graph attention network, and why graph attention network work. Graph attention network is a graph neural network with self-attention. It is a spectral based approach, means it uses only its neighborhood, not that its eigenvalue or eigenvectors for the learning. Graph attention network architecture is made after the great result of attention mechanism in machine translation. During that time, it released in 2017, and during that time, self-attention is on, it provide great results in the machine translation. After that, why not we apply the same self-attention in the graph? So that's how graph attention network developed. Before going to the graph attention network architecture, we'll take about what is self-attention. Self-attention is a mechanism that allows with important of neighborhood node differently. Let's see how. Let's say you have these nodes. Let's change to pointer. Let's say you have this node 1 containing H1 feature vector. So let's say you have a node of 6, 5, 4, 3, 2. These are neighborhood, but you don't know how this information affect this. So let's say in the first you give attention to this node, and in the second here you give attention to this node. Turning it further and further, you will get accurate result of which one should be give how much attention. Here they use softmax for attention. They have used softmax. How we calculate softmax? Let's see. Let's say we are calculating attention how to give the node 2. How much attention we should give to node 2, and we will calculate that by softmax. Let's say we will talk about how feature of node 2 will affect the feature of node 1. To calculate that, we are taking softmax for the attention mechanism. So we will take node 2's feature, we will apply some weights, we will see later. We apply this node's feature by some transformation and do some transformation, and we will take all these 6 node feature and their transformation as in denominator. In numerator, we will take these nodes features like node 2 feature, because we are calculating attention for the node 2, and in the denominator we will take the whole 6 nodes attention. So that's how attention works. The attention mechanism is applied in shared manner to all the edges. Hence, it does not depend on global structure or feature of all the nodes. Means it is generalizable. We can get the accurate embedding for an unseen node. We will see how attention mechanism applied in shared manner. So let's say here in the softmax we will see this gets some type of attention. this gets some type of attention. If this attention, these nodes contribute much, like its numerator is higher than this, then this node 2 will get much attention. So that's how it can travel. By learning the parameter, we can change the attention. And there is also a head concept. We'll see later. That also helps to share the attention. Now we'll see how graph attention network architecture is. These are pretty important when you consider of like making implementation purpose. Like when we try to implement this attention, these features like these dimensions are really important, because if you don't get it right, it will eat your lot of time. So this is pretty important if you try to build from scratch, or you can say we try to implement this paper. Here we consider H is a node feature set. Like if we consider that our graph have n number of nodes, then our feature vector for that will be a set of feature. H will be a set of feature vectors of nodes which are of dimension f. Like our h1 vector consists of f number of rows. Like it will, and our feature matrix will be n cross f. So we can change our output dimension by h dash, which will be of f dash. Here in the graph attention network, we can change our output dimension. So let's say we are taking f dash, so it may be similar, it may be equal to f, or it may not. So we are taking this as f dash. So this will be our output vectors for all the nodes. In general case, we are calculating EIJ, how to give attention at node Y to the node jth, which jth node is belong to the neighborhood of Ni, node of i's neighborhood. So we are calculate that by, we will see here, this is Eij. We are calculating its alpha by applying softmax. Before that, let's say we take this as a E12. So we are calculating at H1 node or the H2 node. So here we will have this W is a vector, like this W is learnable parameter which belongs to f dash and f. We have f dash cross f dimension, and here we have some sort of attention function which will take this weight into hi vector and weight into hj vector, and we calculate attention by that. What attention will take? Attention will take these two, like these two vector of rf dash, and it will produce some. So here rf dash is by calculating these two, we get a vector of rf dash, and by calculating these two we also get a feature of RF test. So that's how it calculated, and here we are considering alpha ij, but here we simply use softmax on the eij. So here we can see alpha ij will be equal to e to the power eij, e to the power exp means exponential. So it's e to the power eij and will be equal to summation of k belongs to neighborhood node of I. For each k which belongs to neighborhood of I, we'll calculate its e to the power eik. So that's how softmax works in the general case. But for the simplicity for the ease of calculation, we have taken alpha ij equal to exponential of Liquid-Lu. We apply some nonlinear and we apply a vector and we concatenate these two, like we are applying some sort of function, but here we are concatenating these two and we simply multiply a vector, where our a vector will be of 2f dimension. Concatenating these two, we get 2f dash number of features. That's why we use a vector, and here we simply apply transpose to like multiply to correct the dimension and multiply it. So here we will see exp of this whole, and we calculate same. We see here k belongs to neighborhood of I, Liquid-Lu transpose H I vector concatenated with W into H k vector. So that's how we calculate for each S, like this alpha ij will be equal to number of S we have, but we are not calculating for each node and each edge. So here we use mask attention. They only compute alpha ij for the nodes j belongs to ni. Like we only calculate alpha ij for the nodes for n. Let's say these two are not connected. We will calculate alpha ij like 1, 2, or like for these two only. We will apply some mask like this. We will apply some mask like these two will computed and these two will not computed. Let's say these two will, if we mask have 1 in here, these two cases, like in the adjacency matrix, we will have these two as 1 and we put this as 0 because there is no edge between them. If we take, there is no such edges. So that's how mask attention works, where J's are exactly the first order neighborhood of I and I included. Here we have also taken our hope equal to 1. The graph says we already talked about what are hopes, like its immediate neighborhood. So here we only take its immediate neighborhood where hop equal to 1. the graph attention network. So our output vector of Hi will be equal to sigma some non-linearity into summation of j belongs to Ni into alpha ij into w into hj. So that will be our update version of embedding for the node 1. So remember that we are all talking about its embedding. We use multiple heads to stabilize the self-attention process. Like we have seen in transformer, like we apply multiple heads to get the different type of information, which also is similar to applying different types of filters in convolution. So we will use different type of heads to get stabilize the self attention. Like sometimes it's attention, let's say in the first head, this way our attention mechanism provide these two nodes much attention, but in the second head, let's change the color. In the second head, let's say our attention mechanism, or you can say head, provide these two as important attention, provides more importance to these two nodes, like provide much attention to these two nodes. And let's say in the third head, it may provide this, it take with these three as attention, like provide more attention to these three. So we'll have different types of heads. So we can generalize the attention mechanism. Like after that, we have concatenated the k. Like let's say we have k number of heads, so we concatenate with this. Like we concatenate all the embeddings of all the head. Concatenation is not sensible if self-attention layer is large, so we use average. Let's say we are calculating our self-attention in the last of the layer. Like there is not much learning layers. Let's say we have a self-attention layer here, and we will use direct prediction layer here, and there is no network here. Like there is no layer here. Let's say there is no learning here, learning parameters here. Like we don't have any layer, like linear layers like this. So in that case, concatenation is not sensible. So we average out all the heads result, and we will use the prediction layer. So that's how we average out, and after that we apply some nonlinearity and then predict. Comparison to previous one, they are already present graph sets, graph convolution network, and many more. If you are much interested in timeline of the how the graph neural networks are released in the timeline version, you can read the graph tensor network paper. In the introduction, they provide the whole graph neural network and when they are got released. So that will be helpful if you are much interested. Computationally, it is highly efficient. The operation of the self-potential layer can be parallelized across all the edges. So here we can, in the graph attention network, we can parallelize, like we can use GPU for computing all the edges, like attention in the all the edges, and we can also use its different head as different type. So like say right here, let's say we have these threads, like threads. Here, let's say we are calculating some batches here, like some batches are calculated here, maybe of head 1, and some batches here of head 2, like all the edges, like say here's some sort of all the edges here, and let's say, and here let's say a second batch of head 1, like some edge in head 1. Let's say it's E1, 2, let's say E3, 5, let's say E2, 4, that type of. We are calculating calculating this parallel. We calculate the whole all at once. The computation of output feature can be parallelized across all the nodes. So we can parallelize across all the nodes. It will be parallelized across the edges, like we have seen. All computation of all edges can be calculated by this, and we can take node and parallelize it. So let's see. Let's say you have this thread or computation cluster. This. Let's say we take node 1, and here we take node 2, and here we take node 3. So we can calculate its node 1 neighborhood and its all. So here we can calculate node 1's neighborhood, like we can calculate nodes 1 embedding, like its whole. Let's take its node 1's here. We talk about node 1. It is neighborhood of this all the 5 nodes. So we calculate here for node 1. Let's say we consider node 2. It only have this connection. Let's say another connection is this. This is another connection. So in the thread 2, we contain these 2 nodes as its neighborhood node. Here in the node 2, this will contain only 2 nodes, like the embedding of node 2 and node 1 and node 3. So that's how we can parallelize across the node also. GAT assign different importance to node of same neighborhood, enabling a leap in model capability. So we have seen it can assign different importance to the nodes. Like in the top sets, we try to sample and infer, but here we use different type like attention mechanism achieves the same type of you can say value result, like generalize for the unseen nodes. So in the graph sets, we use sample and aggregation. In the graph attention network, we use self-attention to increase the model capability. Graph sets samples a fixed size neighborhood for consistency, but this limits access to the full neighborhood during inference, not in GAT. Like in graph sets, we only take a subset of its neighborhood. Like they are always similar, but not the whole. But here in the graph attention network, there is no such limits. Like we can take whole neighborhood as its input. For the dataset, we have taken 3 constructive graph datasets like Bora, Sitesar, and PAM. One inductive graph dataset which is protein-protein interaction. You can learn about much in the paper. If you try to read, I will provide it in my description. Experimental setup. We have taken 2 types of datasets, so we will have 2 types of learning also. In the constructive learning, they apply, like in the paper, they apply 2 layers of graph attention network model. First model and first layer consists of 8 heads. Like they apply 2 layers of graph attention network and each consists of 8 heads. Hyperparameters are optimized with Cora dataset and reused inside. Like first they have trained graph attention network with 8 head in the Cora dataset and get the hyperparameters and then train on the same hyperparameters in the Sitesar dataset. And in the model, they have used exponential linear units for nonlinearity. In the inductive learning, they apply 3 layers of graph attention network. Model first 2 layers have 4 heads. First 2, like in the model, first 2 layers have 4 heads. For that, they apply some ELU for nonlinearity. Like here are the same. They have introduced 3 types of variation. Like first one is graph sets. First one is graph sets. Second one is constant attention on the graph attention network and variable attention graph attention network. So that's the experimental setup. And here we have seen its results. In the constructive learning, they have applied GNN64. Like they have tweaked the graph convolution network and here get this type of results. or you can see GNN perform on the form data better, like similar to GNN64 and graph attention network. Here you can see, you can pause and see. Okay, here are also they have tweaked the graph sets, which provide the result of 0.768 and constant gated graph attention network. Here 93% errors, and the non-constant portion it provides 2.973 with variable of 0.004. So that's pretty high. So you can see overall it can be state-of-the-art performance of previously existed models. Graph attention network is a novel convolution style neural network that operate on graph structure data leveraging masked self-attention layer. Like by applying masked self-attention, it only calculates which are important for that mode, not the whole. So it will reduce the computation, and it is similar to convolution style neural networks. It does not depend on knowing the entire graph structure upfront. You can come up with a different node, like we have seen transductive, like we have seen 3 transductive dataset where the graph changes after time, like it's in dynamic in nature. Still, there are potential improvements like interpretability, incorporate edge feature, and handling large data size. Here are some limitations of graph attention network where we can think of about its interpretability, like how it come up with that result which it have providing, and in that time they have not included the edge feature. But if you take about Python geometry, they have solved this problem, and graph attention network can incorporate edge features. You can read introduction part of graph attention network paper to get clear picture of timeline of graph models releases, like I have talked about just a little bit before. So that's it for today. Okay, now start summary. First, we have talked about what is graph attention network, like it is a neural network with attention, and we talk about what is self-attention, and we have seen the graph attention network architecture, like why it's work, how it's work, like how we calculate its attention, and after that we have seen some of its advantages on the previously existing models, and how it overcome with the challenges that were exist in the previously existing models. After that, we have talked about its like dataset. It takes 3 transductive dataset and 1 inductive dataset. 3 transductive are Cora, Sideser, and Pump, and in the inductive we take protein interaction dataset. After that we have seen what is experimental setup, and after that it's result. That's it for today. Thank you.